Hello, this is Dr. Hanaa Assil, and this is Unit 4, January 2022 in the A2 Edexcel Chemistry. Let us take a look at the questions and discuss the answers. So the first question says, a simplified Born-Haber cycle for the formation of lithium iodide is shown. The enthalpy change of atomization of iodine is plus 107. And it is given by what equation? So when we say enthalpy change of atomization, what does that mean? Remember that the standard enthalpy change of atomization is the enthalpy change that takes place when 1 mole of gaseous atoms is formed from its elements under standard conditions. So first of all, we want to form 1 mole of gaseous atoms. So my answer is A or B. Now, from what? From the element in its standard condition. We're starting with iodine. What is the standard condition for iodine? That is the condition at room temperature and pressure. Iodine is a solid. So my answer is B. My answer is B. Okay. Use the information in the cycle to calculate the electron affinity of iodine. First of all, let's revise what do we mean by electron affinity. Electron affinity is the enthalpy change when 1 mole of electrons is added to 1 mole of gaseous atoms to form 1 mole of gaseous -1 ions. So in the cycle, we have iodine as a solid changing to iodine as a gas. That was atomization. Now iodine as a gas going to I minus, that is electron affinity. So he wants us to calculate electron affinity. You should look at the direction of the arrows, and you should realize that all the arrows going up and to the right are equal to the minus 270. So from that calculation, you can get the value for electron affinity, and that comes out to be minus 298. Some energy changes are given in the table. Use these data to calculate the enthalpy change of hydration of calcium. So you should realize he has lattice energy and the enthalpy of solution and enthalpy of hydration. You should be able to draw this kind of cycle where we start with calcium chloride solid. Now, to make it into aqueous ions, that is delta H of solution. To make it into gaseous ions, that is minus of delta H lattice, because delta H lattice is from gaseous ions to the solid. And then to change the gaseous ions to aqueous ions, then that is delta H of hydration. So following the direction of the arrows, you should be able to get that delta H of solution will be minus delta H lattice plus delta H of hydration of the calcium ions plus twice the delta H of hydration of the chloride ions. And putting in the values that he has in the table, you can calculate for the delta H hydration of calcium ions, and that comes out to be minus 1650. This question says the reaction shown is at equilibrium. The forward reaction is endothermic, which will increase when the temperature is lowered. So the forward is endothermic, and that means the delta H for the forward reaction is positive, and that means when we increase the temperature, the equilibrium shifts to the left. Now, when equilibrium shifts to the left, which of these will increase? Now, he's saying the mole fraction of carbon dioxide. Yes, because we will be forming more carbon dioxide, so that will increase. Now, partial pressure of carbon monoxide, that will decrease. The rate, we were lowering the temperature, the rate will decrease. The value of Kp, if we're going backward, then the value for Kp will be less. Okay, at 680 degrees Celsius and 180 M, 52.6% of the molecules our carbon monoxide. What is the partial pressure? Now remember, if we have 52.6% of the molecules, then we can say that the partial pressure of the carbon monoxide is 0.526, and that means the partial pressure of the carbon dioxide is the rest of 1. So it's 1 minus 0.526, so that is 0.474. The equation for the precipitation of lead chloride is shown. What are the units for the equilibrium constant? Okay, let's write the equilibrium constant. You know that the equilibrium constant, first of all, does not include solids. And then it is usually products over reactants. But because the product here is a solid, so that is not included. So it's actually 1 over lead-2 plus, concentration of lead-2 plus times concentration of the chloride ions to the power 2. So if you put in the units, remember that each concentration is mole per decimeter cubed. So the concentration to the power 2 will be mole to the power 2, decimeter to the power 6. Canceling what is the same up and down, that will give you decimeter to the power 9 times moles to the power minus 3. An example of a diprotic acid is cis-butene dioic acid. Titration of this acid using sodium hydroxide gave the titration curve shown. Which indicator would be most suitable for measuring the endpoint of the neutralization of the proton in cis-butene dioic acid that has a pKa of 6.33? Looking at the graph, you can see that we need an indicator that will change color in this range between pH 8 and pH 11, for example. So using the data booklet, we look at the choices that we have, and the one that changes in that range that we want is phenolphthalein. At 25 degrees Celsius, the pH of pure water is 7. At 100 degrees Celsius, the pH of pure water is 6.14. What can be deduced from this information? So we're talking about water. Water can dissociate to give H plus and OH minus. And he's saying at 100 degrees Celsius, the pH is, at 25 degrees Celsius, the pH is 7. But at 100, that means he raised the temperature. The pH is lower. That means what? That means we have more acid. It is more acidic, and that means the equilibrium shifted to the right, or the reaction favored the forward reaction. So if we raise the temperature and we go forward, that means it is endothermic, and that means we're looking at a reaction that is endothermic. As I raise the temperature, it goes forward. That means the forward is endothermic, and that means I have more H plus ions at 100 degrees Celsius than at 25. That makes it more acidic, so lower pH. The anti-inflammatory drug ketoprofen has the structure shown. What is the molecular formula of ketoprofen? This should be an easy question. When you look at these structures, this is what we actually have. At each junction, we have a carbon, and each carbon should be bonded to a total of 4 bonds. So if it doesn't have 4 bonds, then the fourth is a hydrogen. If you count all the carbons, hydrogens, and oxygens, you will find that we have C16, H14, and 3 oxygens. So that is my molecular formula. Menthol has a number of medicinal uses. It can be extracted from the peppermint plant. The structure of menthol is this. How many chiral centers are there in one molecule of menthol? Remember that a chiral center is a carbon that is bonded to 4 different groups, or 4 different atoms. So where do we have chiral centers here? These are the chiral centers that we have. Remember that if they don't have 4 bonds, then the fourth is a hydrogen. So that means I have a total of 3 chiral centers. Which of these reactions does not result in the formation of a racemic mixture? What is a racemic mixture? A racemic mixture is one in which we have 2 optical isomers that rotate the plane of polarized light to opposite directions. Okay, so that means in order to, if I don't want a racemic mixture, that means I don't want the formation of a chiral center. So he's saying which of these does not form a chiral center. So let's take a look. Butene plus HCl. Do I have a chiral center? Yes. Then this would form a racemic mixture because the chloride ions and the H plus and so on will attack. Remember that a double bond is planar and the nucleophile can attack from either side. So I will have the 2 optical isomers of the product. The same with this. But1ene with HCl will give a chiral center. So I will have, and the double bond is planar, so I will have both optical isomers that will form a racemic mixture. Propanal with HCN. Yes, I have a chiral center. Propanone with HCN. No, I don't have a chiral center because the carbon is bonded to 2 similar methyl groups. So this will not give something that is chiral. It will not give a racemic mixture. When a single enantiomer of 2-iodobutane reacts with sodium hydroxide, the product is a mixture of enantiomers. This is because what? Okay, let's take a look. 2-iodobutane. Remember that 2-iodobutane is what kind of halogenoalkane? It's a secondary. And the secondary can either do an SN2. So in this kind of reaction, this is an SN2. And the SN2 gives only one and one of the enantiomers, or one isomer. But if we have SN1 is where the iodine is released to form a carbocation, and then the hydroxide ions can attack from both sides to give 2 enantiomers. So this will give a mixture of enantiomers, and that means that for this reaction, the reaction is happening by SN1 through a carbocation. So that is C. How many structural isomers with molecular formula C5H10O react with Tollens reagent? Remember, anything that reacts with Tollens reagent has to be an aldehyde. So he's basically asking you how many structures of C5H10O can be aldehyde. So let's take a look. If you draw the C510O in different forms so that they're all aldehydes, you will have 4 different types of structures. So these are the structural isomers. Propanone reacts with iodine in both acidic and alkaline conditions. The products of the reaction under the stated conditions are what? So if I look at propanone and I react it in acidic conditions, this is the kind of reaction that happens. So I have a carbocation, and then the carbocation is rearranged, and then we have loss of the hydrogen. So in the end, we add the iodine to one of the methyl groups. So my product in the acidic conditions is the CH3COCH2I. So my answer is C or D. What about in alkaline conditions? In alkaline conditions with iodine, this is the one that forms yellow precipitate due to the formation of the CHI3, and the rest of the products include the sodium salt. So my answer in this case is D. Please revise these reactions if you're not sure of them. The rate equation for the reaction between propanone and iodine in acidic conditions is this. The reaction was carried out at two different pH values, all other conditions remaining unchanged. In the first reaction, the pH was 2. Now, in the second reaction, the rate is 1/3 of the original value. So in the second reaction, the rate is 1/3 of the original first reaction. What was the pH of the second reaction? Okay, now we have, what do we have? He said in the first reaction, the pH is 2. Now, if the pH is 2, you should realize that the concentration of H plus ions is 10 to the minus pH, so that is 10 to the minus 2. Now, if we're saying that the second reaction is 1/3 of the rate, that means, remember, the rate is directly proportional to the H plus ions because it is first order to the H plus ions. So if the rate in the second reaction is 1/3, then the concentration of H plus also is 1/3 of that. Now, if this is the concentration of H plus ions, how do we get the pH? The pH is minus log of the concentration, and he wants it in 1 decimal, so my answer is 2.5. Butene 1,4-diol may be converted into 2-oxobutane dioic acid in a two-step synthesis through an intermediate compound W. Identify the intermediate compound and the reagent for step 2. Okay, let's take a look at this. So the first one is butene 1,4-diol. What does that look like? It looks like this. This is the structure that he has drawn up there. So this is butene 1,4-diol. Now he's adding steam and sulfuric acid. So what does that do? You should realize that that should add water to the double bond. So we're adding H and OH to the double bond. So that is the structure of W. So my W is the structure in which instead of the double bond, I have an OH and an H added to these two carbons. Then step 2, what is he doing in step 2? In step 2, he is oxidizing the alcohols, or actually he's oxidizing all 3 alcohols. The ones at the end will form acid and the one in the middle will form a ketone. What is our reagent for oxidation? Hot acidified potassium dichromate. Compound X, C4H10O, is oxidized to form compound Y. Now, compound Y reacts with ethanol in presence of concentrate sulfuric acid to give an ester Z. What could be the formula of Z? Okay, what is Z? If I react something with ethanol in presence of concentrate sulfuric acid, it's giving me an ester, so Y must be an acid. We react acid with alcohol to give ester, so Y is an acid. So X is something that is oxidized to form an acid. Now, looking at the choices, if I start with X like this, then if I oxidize it, it will form this acid. And then if we react it with ethanol, it forms this ester. So which one is the correct answer? That's this one. If you look at all the choices, you first of all must have an ethyl ester, ethyl something, ethyl butanoate. So the only one actually that is ethyl butanoate is C. Okay, which of these compounds is a product of the hydrolysis of this ester by refluxing with sodium hydroxide? Remember that an ester can be hydrolyzed by heating with acid or heating with a base. Now, if I heat it with a base, in both cases, the ester linkage is broken to give an alcohol plus what? If it's acid, it gives an acid. But if it's a base, it gives the sodium salt. So these are my two products. Now, which of these are correct? So the one that has B, in B, that is the alcohol. The acid that he gives in C and the sodium salt that he gives in D, all of them are not the correct structures. In gas chromatography, a gas containing a mixture is passed over a liquid stationary phase. The main reason a mixture is separated into its components is because they have different what? In gas chromatography, we are separating the components based on differences in the forces of attraction to the liquid. So the one that is attracted more to the liquid will go down quickly, or we go through the column quickly and we'll have less retention time. The one that is not attracted to the solvent will go down slowly and will have longer retention time. So they are separated based on forces of attraction to the liquid, not the other choices. In HPLC, the mobile and stationary phases are, so this is high performance liquid chromatography. The mobile phase is a liquid and the stationary phase is a solid. Bromate ions oxidize bromide ions in dilute acid. Experiments to determine initial reaction rates were carried out using different initial concentrations of the three reactants, and he gives me the results in a table, and he's saying the reaction is first order with respect to bromate. So the BrO3 minus, it is first order. Now deduce the rate equation for the reaction. Of course, in order to get the rate equation for the reaction, I have to deduce the order for bromide and the order for H plus. So let's look at H plus. In order to determine the order with respect to H plus, I have to choose two experiments in which the bromate is constant. So in experiment 1 and 2, the bromate is constant. Now, what happens to the H plus? The H plus is doubled. What happened to the rate? The rate is quadrupled or times 4. And that means that with respect to H plus, the reaction rate is second order. Why? Because when H plus is doubled, the bromate and the bromide are constant, the rate quadruples. Now, if I'm looking at bromide, again, I want two experiments in which the bromate, but in this case, we don't have one in which the bromate is constant. So we're going to choose experiments 1 and 3. Now, what is happening to the bromate ions? The bromate ions are times 1.5. The bromide is doubled. The rate is tripled. So that means that with respect to the bromide, it is first order. So that means that when we increase the bromate by 1.5 times, the H plus is constant, the bromide doubles, the rate increases 3 times. So it is 3 times because it is doubled, and then once because of the 1.5 increase in the bromate ions. So based on that, my rate equation is rate is equal to K times concentration of the bromate times concentration of the bromide times concentration of the H plus ions to the power 2. Then he says use the data from experiment 4 and your answer to calculate the rate constant and include units. So we decided that this is the rate equation. We put in the values from experiment 4. Please notice that he specifies experiment 4. So in this case, the rate over the concentrations is equal to this value. So this is the value for the rate constant. How do we get units? You have to decide the units. Each concentration is mole per decimeter cubed. The rate is mole per decimeter cubed per second. Put all of this, cancel whatever is the same on both on top and bottom, and this comes out to be decimeter to the power 6, mole to the power minus 3, and seconds to the power minus 1. Give one possible reason why the rate equation shows that the reaction cannot proceed in one step. Remember that the rate equation includes all of them. And this means I have a large number of particles in the reactants. They cannot all collide in the same time. they have to go in different steps. Propanol reacts very slowly with HCN at room temperature. To increase the rate of reaction, potassium cyanide is added. First, complete the mechanism for this reaction by adding curly arrows. So, where is the cyanide? How does it attack? Remember that it attacks the carbon because that is slightly positive. Using lone pair of electrons, you have to draw the lone pairs and the dipoles on the carbonyl carbon and oxygen. The electrons from the C double bond O goes to the slightly negative oxygen to give an O minus and attach the cyanide. And then the O minus will attack. Oxygen also has a lone pair of electrons. They will attack the hydrogen of the HCN to give the product. So this is the mechanism. Explain why the reaction between propanol and HCN in absence of KCN is very slow, referring to the value of Ka. He's telling me that the Ka is 4.9 times 10 to the minus 10. That means if I have this acid, the Ka is very small. It's that means that the concentration of H plus ions and cyanide ions is very small, and that means I have very little cyanide ions. So if I add the KCN, then the amount of cyanide ions will be more and I will have faster reaction. So the fact that the value of the Ka is very small, that means the equilibrium is way to the left. I have very little cyanide and the reaction is very slow. KCN is a homogeneous catalyst. Do you remember the meaning of homogeneous catalyst? Homogeneous catalyst means the state of the catalyst is the same as the state of the reactants. So the KCN provides cyanide ions, and this is in the same state as the reactants. The cyanide ions are regenerated in the second step, so they speed up the reaction without being used up. And that is definition of catalyst. It speeds up the reaction without being used up. Okay, the organic products of this reaction are enantiomers. Draw the three-dimensional structures of these enantiomers. What was the reaction again? Do you remember? This was the reaction and this was the product. So if I want to draw the two possible enantiomers of this product, this is how we draw the three-dimensional structures. Remember that the thick arrow indicates that the OH is to the front. The dotted arrow indicates that, or the dotted line indicates that the hydrogen is to the back of the molecule. So the OH is in front, the H is back, and then we draw the mirror image. Remember that in order to draw the two enantiomers, you imagine that there is a mirror in between and you have to draw the mirror image of the first enantiomer. This question is about compounds with the molecular formula C6H12O2. Hexanoic acid is a weak acid. Write the equation for Ka of hexanoic acid. So hexanoic acid, if it dissociates, it gives C5H11COO minus plus the H plus. So the Ka is the concentration of products over concentration of the hexanoic acid. Calculate the pH of a 0.1 mole per decimeter cubed solution of hexanoic acid, and he gives you the pKa. How can you get the pH? We use the pKa to get Ka. Ka is 10 to the minus pKa. So in this case, Ka is this number. And then I use this equation. Concentration of H plus ions is equal to the square root of Ka times concentration. So we have the value for the Ka that we got times the concentration that he gives me, which is 0.1. That gives me the concentration of H plus ions. From the concentration of H plus ions, I can get the pH. pH is minus log the concentration, so my pH is 2.94. The solubility of hexanoic acid in water is this. The isomer of hexanoic acid, butyl ethanoate, has a solubility of this. So this is a lower solubility. So he's telling me that butyl ethanoate has lower solubility in water than hexanoic acid. Explain the differences in these data in terms of the hydrogen bonding between hexanoic acid and water and between the butyl ethanoate and water. Well, let's look. What is hexanoic acid? This is hexanoic acid. Okay, now when you dissolve it in water, it will form hydrogen bonds, but you have 2 hydrogen bonds per each molecule. This is what happens for any acid. Any acid will form 2 hydrogen bonds with water per molecule, while the ester has only a double bond O, C double bond O, that will form 1 hydrogen bond per molecule, and that is why the hexanoic acid will dissolve more or has higher solubility. Hexanoic acid forms more hydrogen bonds. It has C double bond O and it has OH that will form hydrogen bonds with the water, while butyl ethanoate has only the C double bond O to form 1 hydrogen bond per molecule, so it is less soluble. Compound A is thought to be another isomer of hexanoic acid. So 10 grams of compound A contains 6.21 gram of carbon, 1.03 grams of hydrogen, and the remainder is oxygen. And he's saying calculate the empirical formula. How do we calculate empirical formula? You should be familiar with this. We have carbon, hydrogen, and oxygen. The carbon is 6.21 grams. The hydrogen is 1.03 grams. Now, the remainder of the 10 grams, remember he started with 10 grams of the compound, so the remainder of the 10 grams is the amount of oxygen. So that is 2.76. Do you remember how to do empirical formula? We divide first by the atomic mass. Carbon is 12, hydrogen 1, oxygen 16. Now, the numbers that come out, you divide by the smallest. And that gives me a ratio of 3 to 6 to 1. Remember that at that point it has to be a whole number. That means my formula is C3H6O. State how you might use your answer and a mass spectrum of the compound to prove that it is an isomer of hexanoic acid. Now, what do we look for in the mass spectrum? He's telling me that the empirical formula is C3H6O. The isomer of hexanoic acid would have a formula of C6H12O2, and that means I can look for the molecular ion peak. The molecular ion peak in the mass spectrum should be that of the C6H12O2. So that is 116, and that is twice of the M over E for the empirical formula, or the molecular mass of the empirical formula. A series of tests was performed on compound A, and he's saying deduce the structure for compound A. Let's take a look at the tests one by one. First, he added potassium pentachloride, or PCl5, and he got misty fumes. Of course, these misty fumes are of hydrogen chloride. Which test is this? You should remember that this is a test for alcohol or acid. So if I have misty fumes with potassium pentachloride, that means I have either an alcohol or an acid. Then he added 2,4-dinitrophenylhydrazine and he got an orange precipitate. What would give you orange precipitate with 2,4-dinitrophenylhydrazine? Aldehydes or ketones. Both aldehyde and ketone would give you an orange precipitate. Then he added Fehling solution and the solution remained blue. So that means that we don't have aldehydes, because aldehydes are the ones that would react with Benedict and Fehling. When he added acidified potassium dichromate, the solution remains orange. And that means it did not oxidize. And that means I have something that cannot be oxidized. We've decided that we have an alcohol. That must be a tertiary alcohol. Test using polarimetry. The plane of plane polarized light is rotated, and that means the compound has a chiral center. So you want to think of a compound with that molecular formula that we had, and it has all of this. It must have a chiral center, a tertiary alcohol, and a ketone. We said it reacted with 2,4-dinitrophenol hydrazine, but not with phthalate, so it must have a ketone. So you need to write this in a certain order of thinking. The misty fumes with potassium chloride indicate the presence of alcohol or acid. Now, reaction with 2,4-dinitrophenol hydrazine indicates the presence of aldehyde or ketone, but no reaction with phthalate, so it's not an aldehyde. This indicates that it has a ketone. Since there are only 2 oxygen atoms, then it must be a ketone and an alcohol. I cannot have an. Then we had no reaction with acidified potassium dichromate, so the alcohol is a tertiary alcohol that cannot be oxidized, and it rotates the plane of polarized light, so it has a chiral center. So if we look at all of this, this is the kind of structure that we can have. Okay, a tertiary alcohol, ketone, chiral center. So this is the correct structure. Compound B, another isomer with the molecular formula C6H12O2, contains a ring of 6 carbon atoms. The carbon-13 NMR has only 2 peaks, one of which is at 69 ppm. Okay, let's take a look at your data booklet. You will find that the one that is around 69 parts per million is an alcohol. And that means that I must have a ring with 6 carbons. So it's a hexane, cyclic hexane. And if I have only 2 types of carbons, then the 2 OHs must be opposite like this. Then one type is the H of the alcohol and the other type is the CH2s, which are all equivalent. Esters are used in flavorings and perfumes. They can be made by reactions involving alcohols. A flask containing a mixture of 0.2 mole of ethanoic acid and 0.15 mole of ethanol was left at 25 degrees Celsius in presence of a catalyst until equilibrium had been established. The ethanoic acid present in the equilibrium mixture required 34.8 centimeter cubed of 2.5 mole per decimeter cube solution of sodium hydroxide for complete neutralization, and he wants the value for Kc. Okay, first of all, let's see what he's saying. The ethanoic acid at equilibrium reacted with 34.8 centimeter cubed of 2.5 mole per decimeter cubed of sodium hydroxide. So we're saying the ethanoic acid plus sodium hydroxide gives this. The number of moles of sodium hydroxide is the concentration times volume. And from that equation that we wrote, the number of moles of sodium hydroxide is the same as number of moles of acid at equilibrium. So after it reacted, what I'm left with is 0.087 mole. So I can go back to my original reaction and start writing an ice chart. So initially, he said he put 0.200 mole of acid and 0.150 mole of ethanol to give 0 and 0. We did not have any of that. Now, the change is related to the coefficients. All of them have a coefficient of 1. So I will have 0.2 minus x at equilibrium for the ethanoic acid, 0.15 minus x of ethanol, and I will form x of the ester and x of water. But he's telling me that at equilibrium, the number of moles of ethanoic acid is 0.087, and that means the x is the rest of it. What reacted is 0.113, the rest of the 0.2, and that means that I can say that what I'm left with ethanoic acid is 0.087. The ethanol is the 0.15 minus 0.113. and I'm forming 0.113 and 0.113, I can calculate the Kc, concentration of products over concentration of reactants. Remember that concentration is number of moles over volume. And what the numbers that we have here are number of moles, but actually the volumes cancel. If I say concentration of each of these, it is number of moles over volume, and the volumes cancel, so I can use the number of moles directly, and that gives me a Kc of 3.967. The enthalpy change for this reaction is small. Explain by reference to the type and number of bonds being broken and made how this might have been predicted. Why would you think that the delta H is small? Because if we look at the reaction and look at the bonds that are being broken and being formed, we find that in the reactants, I have one CO and one OH broken. In the products, I have one CO and one OH made. So actually, we have the same number and same types of bonds are being broken and made. An ester which smells of raspberries can be formed by either of two different reactions. Name the carboxylic acid, alcohol, and catalyst used in reaction 1. Now, what is HCOOH? That is, of course, methanoic acid. What is CH3, CH2OH? This alcohol is, if you draw it out, it is 2-methyl propane 1-ol. Now, what is the catalyst for esterification reactions? You should realize it's concentrated sulfuric acid. Now, he's saying explain one advantage and one disadvantage of using reaction 2. Remember, reaction 1, we're reacting the alcohol with acid to form ester. In reaction 2, we're reacting alcohol with acid chloride. So, our acyl chloride. Explain one advantage and one disadvantage of using reaction 2. Why is reaction 2 better if I'm talking about advantage? Remember that using an acyl chloride, the reaction is faster at room temperature, so there is no need for catalyst or heat, so that is less expensive. Or we could also say that the advantage of reaction 2 is that it is a reaction that goes to completion. It's not reversible. It goes to completion, so higher yield of ester would be obtained. Now, what is the disadvantage of reaction 2? The product in reaction 2 is HCl, hydrogen chloride. Now, hydrogen chloride, if it dissolves in water, it forms acid, which is corrosive. Or you could say as a gas, it is toxic, and I will have to do the reaction in a fume cupboard. The equation for formation of ammonia in the Haber process is shown at 298 Kelvin. The standard entropy change of the system is minus 98. Calculate the standard entropy of 1 mole of ammonia. Remember that the delta S system is the S of the products minus the S of the reactant. So I'm trying to get S of ammonia. I can put in the other values. You rearrange the equation to get the S of ammonia. The value of the total entropy change, delta S total, varies with temperature, and he gives me the different results at different temperatures, and he's saying plot a graph of delta S total against 1 over T and include a line of best fit. When we plot the points, we will find that they look something like this. And when we join, this is the line of best fit. Please try to plot these graphs very accurately and pay attention to the points. The relationship between delta S total and 1 over T can be found by combining the two equations. We know that delta S total is delta S surroundings plus delta S system. Delta S surroundings is minus delta H over T, so the delta S total is minus delta H over T plus delta S system. Now, the first question says, determine the gradient of the line including units. Okay, how do we get gradient? You should realize that you use as much of the line as possible, and it is the difference in the y-axis over the difference in the x-axis. That comes out to be around 44 depending on your graph, and the units of course would be kilojoule per mole. Then he says, identify the thermodynamic quantity that can be obtained from this gradient. Well, let us look at the gradient. The gradient is the delta S over the 1 over T, or versus 1 over T. So actually, the thermodynamic quantity that I can get is the delta H. Determine the temperature at which the reaction ceases to be thermodynamically feasible. Now, when does the reaction stop being feasible? It is when the delta S is 0. So, where in the graph do I have delta S total 0? The line crosses at 0 at about 1 over T of 0.0022. That means my temperature is 1 over that, and that is a certain temperature in degree Kelvin. The industrial synthesis of ammonia is carried out at pressures of about 20,000 kilopascal and temperatures between 700 Kelvin and 750 Kelvin. These temperatures are higher than the answer to C3. We said, remember we said that these are higher than the temperatures which we calculated, which is about 450 something. Now, state the relationship between the total entropy and equilibrium constant. What is the relationship between delta S total and the equilibrium constant? You should know that delta S total is equal to R ln K. So calculate the value of the equilibrium constant, the value delta S total he gives me to be minus 37.7. R, of course, is 8.31 times ln K. So I rearrange to get ln K, and then that means I can get K, which is inverse of natural log, and K comes out to be this number. Explain why delta S total decreases with an increase in temperature. We just said that delta S total is R ln K. So if the delta S total decreases, we said the K, what happens to the K? If the K decreases, that means we already know that the reaction is exothermic. So at higher temperatures, the equilibrium shifts to the left. The forward is exo. So at high temperature, the equilibrium shifts backward or to the left. That means K will decrease, and that means delta S total will decrease. State how the Haber process is made economically feasible. We're just saying that it is not feasible, but unused reactants are recycled and the ammonia is removed as it is formed to force the forward reaction. That's how we get more and more ammonia. Ammonia from the Haber process reacts with acids. With phosphoric acid, a number of products are formed. One of these is the fertilizer diammonium hydrogen phosphate. So write an equation for the production of this fertilizer. So we're writing an equation for what? Ammonia plus phosphoric acid to give diammonium hydrogen phosphate, and don't forget to balance the equation. Write an ionic equation to show that ammonium ions are acidic. Well, ammonium ions, if you put them in solution, they will dissociate to give ammonia plus H plus ions. So this forms an acidic solution. A solution containing both ammonia and ammonium ions acts as a buffer. Explain using a relevant ionic equation the effect of adding a small amount of acid. So I have in my solution ammonia ions and ammonium ions. Now, if we add a small amount of acid, that means we are adding H plus ions. This will cause the equilibrium to shift to the left to use up the extra acid. And the amounts of ammonia and ammonium are high, so this will cause only a very little change in their concentration, and at the same time we have used up the excess H plus ions. Okay, that's the end of this paper. I hope this was useful to you, and thank you for listening. Okay, where are the gradient of the line? Well, the gradient of the line, you take as much of the line as possible, so the gradient is 44.4.